Solving systems by substitution. At the end of this lesson, you should be able to answer the following two questions. Why is it necessary to have more than one method to solve a system? And then how do I use substitution to solve a system of equations? So we've previously looked at graphing to solve a system. So on the screen, I'm going to show you the solution using the graphing method. So y equals 2x minus 3 is shown in red, and y equals 1/2 x minus 4 is also, that one's shown in blue. If you look at where they intersect, what you should notice is it's difficult to see what that ordered pair is because the intersection is not at an integer value. So when it's at a fractional value or decimal value, without a more specific algebraic method, it's very difficult to make a graph accurate enough to see the actual solution. So let's consider a second algebraic method known as substitution. I'm going to start with a simple case. One line is y equals 7 and the other is y equals 2x minus 3. What the substitution method states is, if y is equal to 7, I can take that value and plug 7 in to the other equation. Take out the y, put in 7 in its place, and what results is I have an equation in just one variable. So I'm going to solve by adding 3 to both sides. I get 10 equals 2x, so I divide both sides by 2, and I get x equals 5. So I know that the point of intersection is going to be 5, 7. It's where those two lines must intersect. And let's verify this by looking at the graph. So here I can see that they do intersect at the point 5, 7. So both methods are going to give you the same solution. Let's do a practice problem where this time I'm not given exactly what y is equal to, but I'm given an expression. But the process is the same. So I'm going to plug in the expression 2x plus 3 in place of y into the opposite equation. This again results in an equation in one variable, so I'm going to solve for x. So I'm adding 3x to both sides, which gives me 5x plus 3 equals 2. Then I subtract 3 from each side, and I get 5x equals negative 1. Divide both sides by 5, and I get x equals negative 1/5. To get y, I have to do a second substitution. I'm going to plug the negative 1/5 in for x into either one of the equations. I selected the top one, which gives me y equals negative 2/5 plus 3. Which results in y equals 13 over 5. So this solution to the system would be, this results in y equals 13/5. So as an ordered pair, my solution would be negative 1/5, comma 13/5. So this is a prime example of one where graphing would not be a good method because you get fractional values for your point of intersection. Now, in this second practice problem, the one variable, the second equation is solved for y. So I am going to take negative 2x plus 5 and plug this in for y into the top equation, which will give me 3x minus 2, and instead of the y, I'm going to open up parentheses, and in place of that, I'm plugging in what y is equivalent to, the negative 2x plus 5. So again, I have an equation in one variable. So I'm going to distribute the negative 2, which results in positive 4x minus 10 equals 4. I'm going to combine my like terms. Now add 10 to both sides, which gives me 7x equals 14. So I divide both sides by 7, and I get x equals 2. So I'm halfway there. I know x is 2. To get my y value, I'm going to plug into either equation. I'm going to choose the bottom one because it's simpler. Y is already isolated. So I'm plugging in 2 in place of x, which is negative 4 then, plus 5 would be positive 1. So the point of intersection would be 2, 1. Now, what if neither variable is isolated in the equations that you're given? Well, in this scenario, what I do is I scan the two equations and I look for one where the coefficient would be 1. So I just highlighted that y to show you that that has a coefficient of 1. So I'm going to solve this top equation for y by subtracting 2x from each side, which will result in y equals negative 2x plus 2. Now I can take this and plug this in for y into the opposite equation, which would be 2x minus 2. I'm going to open up a set of parentheses, and in place of that y, I'm plugging in negative 2x plus 2. So again, I'm going to need to distribute the negative 2, which gives me positive 4x minus 4, combine my like terms. Now add 4 to both sides, which gives me 6x equals 12. Divide both sides by 6, and x is equal to 2. To get y, I need to plug in, and I'm choosing to plug back in to where I'd already isolated y. So I'm plugging in 2 in place of the x, which is going to be negative 4 plus 2. So y will equal negative 2. So these two lines, I could verify that they intersect at the point 2, negative 2. Okay. This next one, try this one on your own, except I just noticed that there is a t right there, and that should be a y. Try this one on your own, pause the video, and then let's see if we agree on our answer. You should have gotten negative 1, positive 1 for this one. Let's do one more like this, where again we're going to have to isolate one of our equations for a variable. So I'm going to take the top one and I'm going to solve this top one for y. So I'm going to add 4x to both sides to isolate the y, which gives me 2y equals 4x. Now I'm going to divide both sides by 2, so y is equal to 2x. Now I can take this and plug it into the opposite equation for y. Make sure you always plug into the opposite equation, or you're going to cause the equation or the system to look like one of the special cases that we'll look at next. So this is 10x plus 6x equals 8. Combine my like terms. 16x equals 8. Divide both sides by 16. And x equals 1/2. Now I'm going to take this. It's going to intersect at 1/2 somewhere. And I'm going to plug this in to my first step where I had y equals 2x. So I'm going to do y equals 2 times 1/2. Therefore y is equal to 1. So my system has a solution of 1/2 1. Now, let's look at two special cases. Remember that two lines can intersect, or they could intersect and have infinite solutions, or they could be two parallel lines where they don't ever intersect and therefore have no solution. So let's look at how we identify that if we're not graphing them. So again, using substitution, I'm plugging in 2x minus 4 in for y, which gives me 2x minus 4 equals 2x plus 8. So I'm going to solve by getting my variables together by subtracting 2x from each side. And what happens is I get negative 4 equals 8. Ask yourself, is this a true statement? Well, no, it's not. Negative 4 does not equal 8. So this is a case where there is no solution. If you think about it, this would mean that your lines are parallel. And if you examine the original problem, you can see that they had the same slope, which should confirm to you that you've done this correctly, that they are parallel lines. Now, let's take a look at the other scenario. When I examine this, I see that I have y equals x plus 2, so I'm going to take this and plug in for y, which gives me negative 3x plus 3. I open up my parentheses equal to 6, and I'm substituting x plus 2 in place of y. This results in negative 3x plus 6 equals 6. So I combine my like terms, which causes my variables to disappear, and I get 6 equals 6. Ask yourself, is this true or false? Well, this is a true statement. So this is a scenario where there are infinitely many solutions. Specifically, they would be coinciding lines, where the one line falls directly on top of the other, so every ordered pair that falls on the line y equals x plus 2 is a solution. So if your variables drop out and you have a false statement, like the one on the left, it's no solution. If you have a true statement, there are infinitely many solutions because it would be coinciding lines. So hopefully you can now see why it's necessary to have a second algebraic method to find the solution to a system, and that you can explain how to do this.